Hey guys, and welcome to Chem Squad Chemistry. Today you're with Mr. Mullins, and we are going to be covering solutions as well as colligative properties of different liquids. So you are going to need your unit book, and we are going to be starting on page 1. If you've not already looked over these slides, please go back to the website, click on the slides, and make sure your notes are filled in. Today we're going to go rather quickly and talk about only the highlighted points. So starting on page 1, the first thing we need to know about is a solution and what a solution is. You can see here that a solution is a homogeneous mixture. Homogeneous means that it is the same throughout. So oftentimes you imagine that you have a cup of, like, say, salt water or something similar to that. And when you first put the salt in the water, lots of times the salt falls down to the bottom like this, and it's not mixed up evenly. That would not be considered to be a solution because it's not homogeneous. Once you get all of that salt to dissolve, then you would have a homogeneous mixture where it is the same throughout. Homo means same, so it's going to be completely the same. From biology, you should already know that solute and solvent are the two major parts of every solution. The solute is a substance that is being dissolved. Lots of times we think of that as like salt, sugar, and many other things. Anything that's going to get dissolved or tore apart while making the solution will be considered to be our solute. The solvent is the thing that does the dissolving, so you might want to take note of that. Does the dissolving. And solvent, there's lots of popular ones, but water is the major solvent. So again, those are three brand new definitions that you need to know the difference between. Here's an example of a solute and a solvent. You can see that we have some KMnO4, which is in the liquid form. Some water, that's the water. And then over here we have some KMnO4, which is the solid. Once you take this solvent and you dump it into that solute, get it all mixed up and all dissolved, then you are going to have yourself a solution. You notice that the water is the universal solvent, and then our solute is getting dissolved. So super easy. Let's just go ahead and identify a few things from this slide. If we take a look at this one on the left, we see that we have some sugar as well as some tea. Which one of these would be the which one of these would be the solvent? Hopefully you thought the tea, because it is the one that's going to dissolve the sugar. So the sugar would be the solute. Over here, the Splenda would be the solute, and the coffee that it's going into would be the solvent. Here we have a package of Kool-Aid, and the Kool-Aid mix would be the solute, and the water jug that you're putting it into, that would be our solvent. So real quick ways to tell the difference between the two. Keep in mind that water is the universal solvent. We call it that because water will dissolve almost anything, and it comes down to polarity. Most compounds that we're going to deal with and want to dissolve are polar. Water is also polar. If you remember back to drawing Lewis structures in the previous unit, we drew water to look like this, and we know that the water is polar because it has lone pairs, right? So these lone pairs allow water to have a positive side and a negative side. This property of water allows it to be able to pull apart other molecules. That's what makes it so good at doing all of the dissolving. So keep in mind that water is the universal solvent because of its polarity. Remember that there are other compounds that are also polar. If you see things that look like this compound is also polar because of the chlorine. Remember that if you have a different compound attached to your central atom, you are also polar. So our chlorine in this case is making it polar. So polar things are typically the best solvents. Here is a little saying that helps us to remember. It's like dissolves like. What that's talking about is if you have something that's polar that you need to be dissolved, you are going like a polar solute. polar solute. You are also going to need a polar solvent in order to get that dissolved. So if you want it to take something like oil and you want it to dissolve it with water, this is never going to happen. The reason why is because water is polar and oil is non-polar. So we would never be able to get these things to dissolve each other. If you want to dissolve something that's polar, you must have something polar. If you want to dissolve something that's non-polar, you need something that's non-polar. So keep that in mind. Like dissolves like. Here we have a nice little cartoon that helps us to remember that. The brown bear up here and the polar bear down here says, "Help, I'm dissolving." But the brown bear responds, "But bears are insoluble." And the polar bear says, "That's easy for you to say, you're not polar." So because this polar bear is in water, which is also polar, he is being dissolved. This brown bear doesn't have to worry about it because he is non-polar. And there is no way that the water can dissolve him because he's non-polar. So we would take something that's non-polar to dissolve him. Now, if I stuck him in some oil, which is also non-polar, he would get dissolved. So that brings about a new vocab word, which is this word right here, the word insoluble. Insoluble means not able to be dissolved. Not able to be dissolved is the word insoluble. So you need to make sure you take note of that. You will be expected to know it. Also, there's another word that's called soluble. Soluble is very similar to insoluble, except it is able to be dissolved. So in this case, we would say the polar bear is soluble. The brown bear is insoluble because he's not able to be dissolved. Lots of times we get the word mixture confused with the word compound, so we're just moving right along. Remember that a mixture is something that is not uniform. And what I mean by uniform is that it's not the same throughout. So I'm going to write that, same throughout. It's not the same throughout. However, a compound, probably remember this from your last test, a compound is always in fixed proportions. It's always fixed ratios. So if we look at an example of mixture, like let's say trail mix, if I had a big box of trail mix and everyone came up and got a cup of trail mix, it would be completely different for everyone because it's not the same throughout, right? Another example of that would be like stainless steel. Stainless steel is a mixture of many different metals, but it's not always exactly the same. A compound, no matter what you do, the compound's never going to change. CO2 will always be a CO2. If you collect CO2 and I collect CO2 and someone else collects it, it's always going to be exactly the same. So there's another two vocab words that you need to keep in mind. But the reason we're talking about this is because lots of times people think that mixtures are only liquids. But you can see here there's other examples, solids and solids like sand. We also just mentioned the trail mix. Solids and liquid like muddy water, you have the solid sand mixed in the muddy water. Solids and gas like smoke, liquids and gas, any type of aerosol or anything you spray. One that was real common to us is this gas in a liquid. Remember, we have the CO2 that's found in our soda, so that's a gas found in our soda. And lastly, we have like a bunch of gases, which is like the air we breathe. So all of those things are mixtures. Don't forget that it does not have to be a liquid in order to be a mixture. Here's just another remembrance that like dissolves like. So polar is going to dissolve polar. So if we need something to dissolve something as polar, it's got to be polar. Moving right along to three other vocab words, we have these words: saturated, unsaturated, and supersaturated. Each one of these words has their own meaning. Unsaturated, you probably remember hearing this from talking about hydrocarbons and how they are not full of hydrogens. In this situation, we're talking about a solution and how much it is able to dissolve. So I'm going to go ahead and number these test tubes 1, 2, and 3 so we can talk about them. In test tube 1, we see that as we add this sugar, the water is able to dissolve it. That tells us that the water is unsaturated, meaning it's not full of sugar. I can keep adding sugar. Imagine if you have a super hot cup of coffee, just pure coffee, and you put 1 teaspoon of sugar in there. The coffee is going to have no problem dissolving that sugar. If I put another teaspoon, it's going to dissolve that. But eventually I'm going to put so much sugar that that coffee is going to become saturated, meaning that it can't dissolve any more sugar. So here in this example, we see as we take the sugar and we put it into the liquid, it's not able to dissolve it. It's saturated. It's completely full of sugar. It cannot dissolve anymore. Lastly, supersaturated solutions are something that is created in a lab. We do this by boiling. As you know, as you increase the temperature of something, you're able to dissolve more stuff. You've probably tried to dissolve salt in water or sugar in your iced tea. And when it's hot, it's a whole lot easier to do that. So in order to make a supersaturated solution, what we do is we take a saturated solution and we heat it up. And we heat up that saturated solution, and as we do, we're able to dissolve more and more stuff. So eventually, what's going to happen is you're going to add so much of your solute that you're going to start to crystallize your liquid. Sometimes you can actually make there be more solute than there is solvent. And you can tell this because of the creation of crystals. So 3 terms. Unsaturated means not to be full of your solute. Saturated means you can't dissolve any more solute. And supersaturated means you have become unstable and you have dissolved more than what you really can, normally because of the addition of temperature. All of these words help us to read our next topic, which is a solubility curve. Solubility curves show us the relationship between solubility and temperature. Something we need to keep in mind is that typically as temperature goes up, solubility is going to go up. Now there's a few exceptions to this. Gases are the exact opposite. Gases, as the temp goes up, the solubility is going to go down. And you can think of this as like if you want to keep your soda that you got from McDonald's good for a long time, the colder you keep it, the longer it's going to stay good. And the reason for that is because that CO2 needs to stay cool so that it doesn't turn into a gas. So as the temperature goes up with gases, the solubility goes down. And you can see that on this graph with these dotted lines. You can notice how it's an inverse relationship. But when looking at the solid lines, we see that they're all increasing, showing us this direct temperature. As solubility goes up, temperature is going to go up. So on this solubility curve, we're not worried about looking at all the lines at the same time. We're just going to look at one specific line at a time. So if I want to talk about, say, KNO3, we're just going to find the line that has KNO3 on it. So if everybody would find the line that says KNO3, you see it right here. So this is the only line that we're concerned about. If we land on the line represents a saturated solution. If you are above the line, you are supersaturated. I'm just going to write super. And if you are below the line, you are considered unsaturated. Let's write unsat. So let's say that I'm talking about, I've got a solution that is 50 degrees, and I want to know how much KNO3 I can dissolve. I'm just going to follow that 50 degree up and come over. It looks like I can dissolve about 90 grams of KNO3. Let's do it for another one. How about you find HCl? So hopefully you found HCl right there. So the only line that we're concerned with is HCl's line decreasing. Shows us it's a gas. And how many grams of HCl can I dissolve at 80 degrees Celsius? So we're going to find 80 degrees, come up to the line. Looks like we can dissolve 50 grams. So our 50 grams of HCl can be dissolved. Now you're going to notice that these units over here are a little complicated. It says grams of solute divided by 100 grams of water. So this is telling me that these 50 grams, I can do that in 100 grams of water. So it's all based off of 100 grams of water. If I dumped 50 grams of HCl into 100 grams of water, I would have to get it up to 80 degrees before it would dissolve. So that's how you read a solubility curve. Down here in this next one, I'll give you a second, pause the video now, and answer these questions. At 15 degrees Celsius, it looks like we can dissolve about 38 grams of that. And how many grams of Ki will dissolve in water?